Welcome to the second introductory lesson on fractal geometry for MGF 2106. Geometry is all around us. We see the basic Euclidean shapes in architecture and in art, in just about anything made or designed by man. But what about the shapes we find in nature? Simple circles and triangles are not sufficient to describe the natural world, and that's where fractals can help. Take a look at the Romanesque broccoli, for example, or the repetition found in this fern. Look at the patterns of a simple ice crystal, or the chambers inside a seashell. The world you know is a fractal paradise. The world, in fact, is full of fractals, it seems. It was Mandelbrot who first proposed modeling a rough terrain that would be similar to the Earth's surface using a fractional Brownian motion. Although these look more like pictures of real life, they are also fractally generated landscapes. Hollywood soon caught wind of this idea, and the generation of natural-looking landscapes created through fractal generations was first used in the early 1980s. You may have seen Star Trek II: The Wrath of Khan. This fractally landscaped planet was created by Lauren Carpenter using a variation of the techniques Mandelbrot developed. To the alien worlds we frequently encounter in video games and film, fractals have found their way into the alternate realities experienced through computer graphics. In fact, with a simple and an often inexpensive download, you too can explore worlds of your own creation, like this one created with LibNoise. There is, in fact, a wide variety of free and paid fractal programs to explore and use to create your own worlds. You can find these with a simple internet search. Fractal art is another fascinating field, and fractal pictures make up some of the most beautiful designs. There are hundreds of examples online, and the book, The Beauty of Fractals, pinpoints examples of this artistic movement. The lines do sometimes get blurred between landscape and art when we talk about fractal images. And as we can see with these pictures, these are renderings of a fractal national park. They're attributed to a 3D app written for Windows called Mandelbulb 3D. The app is described as a mathematical formula visualized with computer graphics, and there are many formulas that can be explored. On a more realistic note, fractals have also been used to describe and explain financial fluctuations. In an article first published by Scientific America in 1999 and republished in 2008, Benoît Mandelbrot explains how a model derived from his work in fractal geometry can create a realistic picture of the stock market ups and downs and their associated risks. An illustration found in this example of a cartoon-type fractal generator shows how our method of producing fractals with replication of a pattern can resemble the changes taken in the stock market. Another slice of the study of fractals is in the field of music. There are different methods to creating fractal music, including one called L-systems. In short, L-systems start with replacing a short string of symbols with a set of rules and repeating this repetition process. The symbols can then be interpreted as notes or chords. The sound of fractal music varies. You may associate this particular tune with some of the scarier movies you've seen. While others, like this one, may sound very light and carefree. It all depends on the rules you've used to replace the symbols, and of course on the order of the symbols themselves. We're going to work on some of the basic concepts behind fractal geometry now, and eventually you will have an assignment that allows you to explore some of the features of fractal shapes. Let's go back and review what you learned in the last lesson with the definition of self-similarity. For our purposes, we will consider an object self-similar if it can be completely divided into parts that are all similar to the original. So we must check for two things. Are all the parts similar to the object we started with, and was it completely divided, which means nothing is left over. Let's look at some objects that are self-similar and some that are not. The triangle, for example, represents an equilateral, but is it self-similar? Well, can you divide it into parts that look just like this one? Well, yes, you can. You can completely divide it into 4 equilateral triangles. And you could continue to divide the smaller triangles the same way an infinite number of times. What about this Sierpinski triangle? You've done the construction of this one, and you should remember that we can keep repeating the construction process an infinite number of times, giving us what we call the limit figure. Basically, that's a never-ending set of triangles in the same pattern getting smaller and smaller. So is it self-similar? Well, I can divide it into like shapes. Remember, the shapes are alike because the limit figure keeps going with smaller and smaller triangles, so each piece does look like the original, no matter how many times I divide it. What about a circle? I can make other circles from this one, and I can keep going. I could make smaller and smaller pink circles, but there is a problem. I'll always have part of my original blue circle left over. Remember our definition. It has to be completely divided, nothing left to be self-similar. So a circle just doesn't work for us. Now, you try it. There's a worksheet on self-similarity. Divide the shapes and discuss why they are self-similar or not. And we'll come back and discuss it when you're finished. Take a look at one of the most fascinating fractals of all, the Sierpinski tetrahedron. A tetrahedron is made of 4 equilateral triangles. It's not a pyramid. With the tetra, any side can be the base. People have been making this fractal design in everything from paper, this origami tetra is one example, to metal. This one is a welded metal structure created by Breckenridge High School in Minnesota, to the most unusual one I've found, made from baseballs, bats, and steel. The Sierpinski tetrahedron gives us a 3D look at the stages in a fractal construction. Count the stages in the Breckenridge High School construction. What do you find? Can you imagine the time and the cost involved? We're going to do some basic calculations that look at constructing different stages of a Sierpinski tetrahedron from paper. And for this, you will work in groups and use an Excel spreadsheet I've started for you. You will either have a 2-inch, 4-inch, or 8-inch tetra as a model. And I want you to work together to fill in the columns of your spreadsheet with the calculations needed to find the length, area, and volume measures for the size tetra if you were to build it into a stage 0 through a stage 10. Now here's an extra credit opportunity. I've placed a short video in Blackboard that demonstrates how to make a stage 2 Sierpinski tetrahedron. You can use my method or you can come up with one of your own. You can also use any materials you like. The construction must be at least a stage 2. When you finish, take pictures and post them to the discussion board in Blackboard, along with a detailed discussion post. How did you do it? What did you learn? That's it. Have fun and build a better tetra.